So, it's a pleasure for me to introduce Anand Periasamy, who made some thoughts about how to bring Linux I/O into the next level, and let's hear his thoughts. Welcome. Where's our sound technician? There he is. Here, one of the guys really working behind the scene all the times, making the technique work. Applause! Jake.
Is it okay now? I did not turn it on. That was the problem. So, I also did not know the previous talk was about Gluster. You will see some references of Gluster here too. The reason for that is I founded Gluster project, and I learned a lot in the process, and you will hear about some of it in this talk. I couldn't have asked for a better home for Gluster. Now that it's with Red Hat, and also there is a vibrant community, they are taking Gluster to the next level. I'm now working on a new open source project. It's actually an open source free software alternative to Amazon S3. I won't talk about that project, but so this one is specific to how you can build large scale storage systems handling petabytes of data in user space. Let me skip this slide. So this talk is not about kernel versus user, which is better. It's no kernel bashing, but this talk specifically talks about, like, back when I started Gluster in 2005, end of 2005, it was really 2006, we were discouraged a lot for attempting to write a file system in user space. Even at a much later stage, Linus himself made a statement about user space file systems are toys. He likely meant about file systems. They are basically root disk file systems inside the kernel, but a generalized statement from him really hurts new projects adopting user space. But we have come a long way today. We no longer have fear of attempting storage systems in user space. The most popular ones, the production grade user space, the storage systems are actually in user space. This talk, I'll address more about how you can build different kinds of storage systems and embrace user space. There are a lot of new advancements since I started Gluster to actually enable user space storage architecture. We'll go through those details in this talk. So the first thing when people think about user space file system is user space file systems are slow, right? Some of the common things I heard when I did Gluster was it will take 10 years to get POSIX right, and there are already other file systems like Lustre, L-U-S-T-R-E, and they would be way ahead of you in 10 years. And my point was that I wanted something that is simple and just works. And by the way, Gluster has nothing to do with the Luster, no code sharing. Even the name, Gluster's name came from GNU cluster, and it was originally supposed to be a user space distributed operating system inspired by Herd, but it ended up becoming a distributed file system, but still inspired by the Herd design. And this was around the early days of Gluster. We were able, to break the idea of that user space file systems are slow, we were able to demonstrate 2 gigabytes per second per node on a cluster. We were able to get a peak on a small cluster. We were able to show 16 gigabytes per second throughput, and each node giving around 2 gigabytes per second. And this was peaking a 20 gigabits InfiniBand card. Back then, 10 gigabit was not ready, but we were able to show that you can actually get full performance close to the network limits. In fact, the disks were able to pump out even more, but the network RDMA, that's the peak we could get. In fact, we were able to do memory-to-memory transfer RDMA all from user space. Right? Back then, it was possible. And one of the recent advancements is DPDK. This is by Intel, and it's also a free software open source project. You can implement user space network. It actually comes with its own user space pole mode driver. So one of the hard things in user space is context switch, right? If you are waiting for the interrupts for each packet, it is very slow. It causes a lot of context switch. But instead, there's a tiny kernel component that interfaces with the user space, so you can dequeue the packet on pole mode. You take a bulk set of packets and process them quickly in user space. So you have an interface for that, and you have a whole. So if you are dependent on TCP/IP stack, you even have a user space TCP/IP stack. You have a low-level APIs to directly deal with the device. There are so many features that now today from the user space you can start doing high-speed networking. To process 80 million packets per second on a single Xeon E3, E5 class processor, it is a big deal. Even the older processor, the previous generation of Xeon, there is a comparison between kernel mode TCP/IP and the pole mode user space driver. You can see between 12 and 35, it's a pretty big jump. But the idea is not to show that user space is faster. It is the idea I want to share here is that user space is not slow, right? Even if it's a matter of writing code, you can, of course, get this kind of performance inside the kernel too. One of the debates early on was that NTFS in user space was faster than the kernel mode file system. The truth is that you can write disciplined code inside the kernel mode. It's just that it is hard. Because user space is easier, you could optimize it and make it better and maintain the code. You end up making user space code faster. But overall, performance is not really important. Writing code and maintaining it is the hardest part, right? Finding bugs, losing data, they are all the important things to worry. And nowadays, the amount of data we are talking about, 100 terabytes is no longer a big deal, right? A single drive today is anywhere between 4 to 6 terabytes for an enterprise-grade disk, and up to 10 terabytes for a desktop-grade disk. The file systems that you are talking inside the kernel mode, they crap out for even 6 terabyte drives. Try doing a file system check on a 6 terabyte drive, you will know how painful it is. When you are talking about a single 2U box with 12 drives, on average, like the Facebook Open Compute box, you're talking about 30 drives in a single chassis. A kernel mode file system struggles to manage that much amount of data, right? But kernel mode file systems are still good if you are talking about root file systems, like a small local disk file system where you want to do low latency, high performance I/O for database workload, things like that. But for the most part, when you are talking about large scale data, petabyte, a single rack can be anywhere between 2 to 4 petabytes of data. For that scale, you just have to move things to user space. Now, file system is not the only part. So there are different types of systems to manage large amounts of data. There is block storage, there is file system, and then there is a new category called object storage. Object storage is somewhere in between file systems and block storage, but I would say object storage is more closer to file systems without the POSIX semantics. It's just a simpler interface, a tiny stripped down version of POSIX, which is just get, put, and list, right? And it's over HTTP. So these three are emerging as the three major interfaces for storing large quantity of data. Within them, there are like so many implementations. These are just like the kernel mode. Not all of them are kernel mode, but I'll go through the list. So GlusterFS you just had heard about in the previous talk. It's a distributed file system in user space. And Hadoop HDFS is basically built for storing large quantities of log files. They call it unstructured data, but any structured data, if you just throw lots of them, it becomes unstructured. So HDFS is another popular large-scale unstructured storage. It is not exactly a file system, though they like to call it a file system. In Gluster, for example, when you say 1 gigabyte file, it is a very large file. On average, files are like anywhere between few kilobytes to few megabytes, and a gigabyte size file is very big. In Hadoop, a file can be even a single, like a couple of terabytes. And when you are having terabyte size file, you are recommended to have a gigabyte size block. On average, if you are talking, you are talking about like 64 to 128 megabyte block size, whereas in Gluster it's 128K. For a disk file system, it's 4K, right? So Hadoop is treating a file as if it's a volume. But when you talk about lots and lots of data, see, you are collecting log files. These are logs produced from machines that are pumping data all the time. Now, whether you store log files 1 per day per machine or 1 per month, it doesn't matter. It's a time series data, right? But it just keeps growing. So Hadoop got rid of the idea of files and files in the context of files and folders and organizing them. Instead, you just dump them as just blocks and blocks of data in a very large file. That's why the file keeps growing. A file in Hadoop is equivalent to a volume in Gluster. Now, NFS Ganesha and UNFS, they are not exactly file systems by themselves. It is a front end for developing file system. They implement the NFS specification. You build the storage system behind it. I'll talk more about them in detail in the coming slides. Now, the block storage part. Block storage, there are multiple interfaces, but to me, the most favorite one is NBD. Because NBD is not tied to the SCSI-like specification. In SCSI, you have like so much of legacy built in. Even though there are so many improvements, SCSI is tied to a consortium of storage industries, and I hate anything that has a big standards body and so many people have to vote. Things move very slowly. It happened even with NFS, right? When we started Gluster, PNFS specification was on paper, but I knew that by the time I see realistic NFS client, Gluster won't make it. So we basically adopted Fuse and we just moved forward with it. We basically said we just want something that is workable today. We actually had a need to take it to production in 6 months, and there was nothing out there. That's when we wrote Gluster, and there was no way we could have waited for NFS specification to stabilize. And with NBD, there is no SCSI things to worry. Even though it borrowed these ideas, but NBD is a simple block device server and a client. There are variations to NBD implementations, like I think BNBD, there are XNBD, there are a few, but the idea is really simple. Now, if you are building a infrastructure like AWS, Amazon EC2 like infrastructure, or a DigitalOcean like infrastructure, the fundamental things you need to worry about is you need to give CPU, you need to give memory and disk, right? Of course, network. Now the disk part, you need to have a persistent local hard disk, whether it's a Docker-based or a Zen-based, any virtualization. Block storage is a fundamental part because they appear as a local operating system drive. And you need to think about how to handle thousands, if not millions, of containers and virtual machines in a large compute farm. How are you going to build a large-scale storage array? Clearly here, any of the industry standard SAN storage array network, the most expensive, highest-end ones from EMC and NetApp, they won't be able to handle the kind of load we are talking about today, right? So I'm just browsing through what possibilities, what we need to solve. We will go into the architectural details of how we can go about solving these problems. Now on the block storage, there are also like LIO, TCM. The LIO project actually is Linux IO. They changed the name to TCM. I think TCM stands for Target Core Module. Any of you remember here PC MCIA? Do you know the expansion? Anyone remembers the expansion? I hate acronyms. Storage industry is full of them. People can't memorize computer industry acronyms. I'm glad that PCMCA died. So SEST, TGT, they're all basically SCSI implementations. There are multiple competing SCSI implementations. These are basically like, they appear as iSCSI. They all started with the iSCSI server. Just like NFS, like UNFS or NFS Ganesha is a user space server that appears as NFS server. TGT, like SEST, all these projects, they appear as if they are an iSCSI server. It's a software server. It makes it look like you are a network disk, right, including NVD. Now, LIO is actually the odd one out of these because LIO is actually inside the kernel. But what they recently did was they exposed the interface. While it appears as an in-kernel iSCSI device, they exposed the back-end part where the actual storage functionality is performed. They exposed that both to the kernel as well as the user space. I like it when Linux kernel allows, like in an unbiased way, that you are free to extend in the kernel or in the user space and not be picky about it, right? Because sometimes kernel mode is great, sometimes user mode is great. By having this option, you are allowing both of the communities to coexist and innovate and let the users choose which one they want. And instead of being religious about user space is bad or kernel space is good. In LIO TCM, it now has interface to bind a file system, a block driver. There is even a driver for Ceph and Gluster. You can now implement storage backends that appear as iSCSI, where to the client machines, the iSCSI server is in the client. Now, DRBD is actually another popular project, and DRBD, it only works like across 2 nodes, but for the most part, that is all you need. When you want more nodes, just have 2 more, 2 more, and 2 more, each serving their own set of users. So it allows like one active server. It basically inside the kernel, it takes a replica into the other node. Now, the third part is object storage. So object storage, there are basically 2, 3, actually there are many, right? So even Gluster has Swift APIs. Gluster is also an object storage. Swift is also object storage. Minio is the new project that I'm working on. It's very early. And then Ceph also has object storage. There are a bunch of projects, but these are all open source. Now, when we started, for Gluster, it was a POSIX compatible file system. POSIX is a very low-level API, and it is very chatty. You cannot possibly use a high-level language like Python and implement a very responsive system. Gluster actually has like all the complicated things you can imagine in a programming environment. It's non-blocking, it's asynchronous, it's message passing, distributed, threaded, all put together, and all these machines in a distributed environment, machines fail all the time. It is a hard part, but possibly solving these problems inside the kernel makes it really hard. Pushing them to user space means any failure, you take failure as normal. You gracefully handle those failures. It was easier to debug, just a standard GDB was fine. In fact, initially even I was kind of resistant to it. Like Gluster official releases were compiled with the debug symbols and released. And the engineer's point was, big deal, it's just small, like little more like stuffing of the binary, but the point is that in a production environment, if it fails, I can attach GDB and see what went wrong. I can fix it. Usually the harder part is not fixing it. It is actually finding what went wrong. You could just like literally compile with the debug symbols and push it out, and users were fine. In fact, what we also did was, Gluster was written in C, and we did not hire C programmers. We were not storage experts, and we did not hire any of these storage experts. There were only a handful of file system hackers that you can hire across the globe, and they came with old aging ideas, and they're very hard to change them. Our idea was that it should look like, while it inherits the ideas from Herd, it should just look like an FTP server. It should look like a collection of web servers. It should not be any more hard. And to do that, all you need is disciplined C programmers. What we did was, we hired Lisp hackers. In fact, we didn't hire, these were the kind of, like my other hobby projects were C and scheme extensible. And these guys were like with a read line. These are like simple, stupid projects like Messenger. I wrote it back when my wife was girlfriend. To talk to her, she used a proprietary messenger, Yahoo Messenger, and then I need to talk to her. So I wrote a C program that was read line extensible, Lisp extensible. So that's how these Gluster guys found each other. They thought it was cool. And these were Lisp hackers who wrote better C code because of the functional thinking. And that helped Gluster a lot. But back then, people did not believe that we could actually solve storage problems in user space. They thought that to build a storage operating system, you need to take a BSD, one of the free BSD, NetBSD, hack it, make a proprietary variant, make specialized extensions, build a specialized hardware, and pack them all together so it's so easy to operate, turnkey solution. They always believed that storage has to be a hardware appliance. They did not believe storage can be a software. And we were like, if I want to put my data, I just want a collection of FTP servers running on a bunch of Supermicro boxes. Why should it be hard? Back then, they did not believe us. We basically pushed to user space, adopted a C language. Only thing we inherited and we had to was POSIX. And it looks like NetApp, but it's just a simple user space server turning a bunch of disks across machines into a big system, right? But after we started, there were newer projects like taking off. The ones that grew after we started prominently were like the HDFS, like Swift. And if you look at them, they were writing code in Python, in Java, and they made us look like we are the old school kernel guys because we are writing code in C. They were able to, the reason why they were able to move ahead was they ditched POSIX. POSIX was the one that was holding us back because it was, you have to be responsive. It's a chatty API. And when POSIX was designed, it was designed for a disk file system. They did not think about a network file system, and network latency is so bad. Possibly we couldn't do that in Python. But Python is not a bad language. Python is very slow compared to C, but Python core parts are in C anyways, and you can always implement core logic in C and embed and extend inside Python. So the flow you can handle in Python. Python, if you are a disciplined programmer, you can write Python code just fine. Sometimes when you do projects in Python, you end up hiring ops guys who can write automation code, and they are not necessarily the best guys to write enterprise grade large piece of software. So I don't blame Python. It is the kind of people you bring on board to write Python code. Like if you got a Haskell guy, like a Golang Java guy to write Python code, even if they have not hacked on Python, you will see them writing better Python code, picking up Python very quickly. That's the beauty of Python. So Python is just fine. Particularly when you're talking about object storage like environment, you're only talking about HTTPS. Your HTTP internet latency is so high, the Python difference will be so marginal you won't even recognize, right? And Java, personally, I don't like Java because of the JVM dependency, and it's kind of blotted. But once it starts, you are just fine. It is pretty close to C++ performance. For long-running tasks, Java is just fine. It's portable, but if you are talking about like Hadoop is a good example, right? Hadoop, they were able to build large-scale systems. In the end, they handle petabytes of data, and what matters is they have a solution that works, and there is so much of Java talent, they were able to manage it fine. But like recently, I heard that like Facebook, they were talking about libnfs. Like there are tools that are redundancy, and using libnfs. Libnfs is a client-side library which is completely user space. You have this tool directly, like you're writing these tools that talk to Gluster NFS server directly. They complete the job by the time the Hadoop-based tools, HDFS-based tools even start loading the jar files and JVM. The Gluster-based tools complete in that same time. It's just lightweight, so C shows that advantage. But if you have long-running jobs, that Java load time will become marginal. But in general, sysadmins, the good part of community, they still have hatred towards Java. So for the new project, I picked Golang. I have a talk specifically about why Minio picked Golang tomorrow. So I'll talk more about it later. But Golang is actually a fine balance between Java, Python, and C. I'm able to basically get it's still not as fast as C, but it gives you the compiled performance, and it's getting better. It is as easy as Python, and while you don't have the JVM bytecode like environment, Golang is just as portable. Our code is just already running from ARM to ARM Linux, like OS X, Windows. It gives me the same advantage of portability, and it's so lightweight. So I got like pretty much best of all the worlds. But again, pick a language depending on what problems, what kind of storage you want to build, what your user base, and what kind of community. The language you pick will also dictate the kind of community you are going to attract into the project. Now, there are some interfaces to do things in user space. Fuse, of course, is the common one, right? When we started early on, people thought Fuse was like writing SSH file system, Gmail file system. It was really for building toys. They did not believe one can write an enterprise-grade, high-performance distributed file system in Fuse. I actually did not know about Fuse early on. Coming from Herd, in Herd, file system namespace is the operating system. It's basically like operating system fits inside the file system namespace. And translators are very natural inside Herd. Everything is implemented as translators. And our original plan was to build something like that for Linux. And there was already Fuse project. And back then, Fuse project was not welcomed inside the community. It was kind of like kept outside. But we liked it anyway. Fuse code was well written. In fact, one of the Fuse maintainers, we brought him on board, and Fuse worked wonderfully for Gluster. But back then, they did not believe you could actually do nice things in Fuse. The network and disk latency are the ones that holds you back. The kernel context switch, that is not a big deal. For the most part today, even in the POSIX world, don't do 4K based operation. If you are doing like around 128 kilobyte like read-write chunks, you will actually see the context switch problems disappear, right? So it's just a matter of how you perform the I/O. The other ones I'll quickly skip through, like Qs or Qs, I don't know how to pronounce it. It's a character interface, like UIO it allows you to actually do memory access, like you can map into a UIO device and you can access specific parts from user space. libUSB allows you to write user space. Pretty much you can access USB devices from user space. They're not so much useful. The three of them are not so much useful for writing storage devices, storage systems, but just to give you an idea that it is possible to implement even like USB stack in user space, right? DPDK and SPDK is actually an interesting one. The DPDK actually has the full-blown. Let me go to the next slide. It's not very clear, but I'll explain to you what it is. Intel released this as a kit, SPDK kit. What it does is, like it has its own, like if you notice, it has a DPDK interface, like it has a NIC driver, like from the user space you can access you can dequeue the packets. You have TCP/IP, you have user space iSCSI, you have like even the newer ones that are coming on board are the NVRAM. Intel actually is now pushing big on persistent memory. It was a dream for operating system guys for a long time. We wanted to basically converge the disk and memory as if they are one. What if the disks are as fast as memory and they are persistent, right? Disks never got as fast, but it now looks like memory can get persistent. It is an answer that Intel is working towards, like compared to solid state, how about we make memory persistent? They are working on some new technologies that are like at nanosecond latency. So soon, like in a matter of 5 years, we will basically see memory 1 TB, 2 TB memory to be persistent, and that is a big deal. That will change. We have to start incorporating those kind of improvements into how you design storage. And now, to access those devices, you now have user space interface. You can directly talk to the persistent memory device from the user space, and even the controller to talk to the persistent storage is now etched into the CPU die itself. So CPU can directly talk to them, and you have a DMA access to the persistent memory. So a lot is changing. Since we started Gluster, a lot has changed, and now it has become really, really easy to do high-speed I/O all the way from user space. CBDMA is also a DMA interface into the storage device, and then there is a memory driver. They also have, like, you can now map an NVM device as if it's a block device and just format with even ext4 and mount it. So there is Mellanox libVMA. It's a library to do user space RDMA between nodes. And you can get real high-speed performance with the RDMA. It works on both 10 gigabit as well as 10 gigabit now is also 40 gigabit, and we are working towards 100 gigabits. InfiniBand is also there. So both of them, you can now do RDMA using this library. In fact, the ones that we followed was just use POSIX standard library. For the most part, users are giving you data in the form of some log files. These are photos, pictures, images. Just take them and store it as a regular file, or even they are erasure coded and sharded on the disk. But you really don't need specialized access to hardware, like I was talking about all these things. You really don't need much help, special help from the kernel, unless you are implementing a special purpose block device or special purpose storage. For the most part, building a large scale file system or object storage, you don't need anything special. All you need is standard POSIX C library interface. In HERD, they used Mach message based APIs, and it was kind of tied to Mach. It was supposed to be portable beyond Mach, but with the Gluster, we just use standard libc APIs. We treated Linux like any other microkernel and just wrote it like a regular any other C program in user space. Same thing goes now for all modern applications. In fact, more and more, when you talk to the application developers writing code in Node.js and Java, they're like, what is FSTab? Why should I be root? They really don't understand these things. All they want is HTTP, get code in and the metadata in the form of JSON. It is just fine for them. So it's really easy to forget about all the low-level interface and start writing like you're writing distributed user space application. We have been through this. So the common pitfalls: don't build very large systems. That's one lesson I learned building large systems, right? Be it a supercomputer or super storage. Building very large systems, again, this means that don't build very large namespace. Building a large namespace, like say, I want a bucket that can store 1 trillion files. I want a namespace that can store billion files that can scan across, that can scale across 1,000 nodes. It actually becomes very unreliable. It's like putting all the eggs in one basket. Imagine if you do DF, it's nice to see a volume that is 10 petabytes, right, 100 petabytes. But in reality, talk to any of these high-end deployments, they're not really building very large systems. They're actually building smaller systems. Almost the scalable unit is like 6-node, 8-node clusters, and that is it. In fact, it's like 4-node. But what do you do when you add more users, more territories as the application scales? So you're like Box.net or Dropbox. What you do is provision a new storage cluster, another storage cluster, another storage cluster. Now, anytime you want to upgrade, downgrade, troubleshoot, heal, replace hard drive, you are only operating on one silo. Right? That becomes very scalable. So the approach to building very large systems is to not build a very large system, but build many smaller systems. But something that I'm now incorporating in the newer ones, right? Again, like avoid massive scale. Also, another thing I saw was it's natural to build systems that once you build a storage system, you see that it's a key value store in the end, right? It can store any kind of namespace. So you want to be file system, you want to be object storage, you want to be HDFS, you want to be NFS, even block storage, container storage for containers. And then they also go on to build, I can even do key value store like databases. It is very tempting as an architect that you solve the hard part, but then now you can, with little more effort, you can build a grand unified storage, one storage system that can be file, block, and object. In reality, it is very hard. You end up building a Swiss Army knife, right? So you don't build a system that does many things, you build a system that builds one thing so much better. And that's again another takeaway for me from my experience. And then performance is not important for the most part. When you're talking about like petascale data, it is reliability and operations. How do you keep your data safe? How, like more and more organizations like Google, if a node fails, if you have to send an engineer to fix it, it's more expensive. It's people cost, that's where you lose money, right? These nodes are cheap. Let them fail, other nodes will take care. Once in a while, you go to data center, pull the machines that are dead and refresh them. Focus on keeping data safe, focus on making it easier, and that's how you scale. Performance is secondary. Particularly when you scale out, you have many processors, many CPUs, and many network. It comes to you as a bonus. It shouldn't be your goal. Unless you are doing some special purpose file system, which is not for scale, focus on keeping things simpler. Avoid complex algorithms, avoid intelligent systems. Something I've learned again hard way, that self-managing systems that are intelligent, that can fix all these problems by itself, it often breaks down. Like most of the time I see, if you set up a high availability network, it needs a secondary network and a tertiary network to reliably detect whether it was a real failure. To check the failure, you have to check on the 2 other networks. And I see that system fails because the setup is so complicated, right? And then like I also see problems like the consensus based, like the Raft protocols, while they are relatively better now, systems are complicated and failing because of these algorithms. Even if I kept the system in a way that if the node died, I just SSH and then restart by hand, I often find those systems to be cheaper and easier to manage than a complicated self-managing system. Now, quickly I'll touch upon 3 architectures. Like say if you're building a file system, if you have a strong reason to adopt POSIX, just use NFS Ganesha. Of course, you can have your own custom proprietary RPC like how Gluster took initially, but there was no NFS Ganesha back then. Instead of saying we can do multi-protocol, stick to one. Just stick to NFS. NFS clients are already there. Even for the OS that does not have NFS client, you have like libNFS. And with the NFS front end, the backend is the one that you are going to focus. And even there, don't build a very large namespace, right? Keep things simple where the backend does an eventual consistency replication. Writing a synchronous replication, Gluster does it, but it is really hard. If you literally, like one of the models in a cloud-like environment is you have many NFS servers where each NFS server is serving a set of users, or even one per user. It's almost like the microservices model. You have like micro storage. Build small storage systems, but in large numbers. And with each user having dedicated NFS server, basically any failure, you just know how to fix it. Literally, you can SSH and SCP the data back, and you are good to go. Things work very well. That's how you scale. You scale up, you turn distributed problems into provisioning problems. Now you can have simple Chef Puppet scripts to basically automate, heal, recover, and it's just a simple problem. Same thing goes to block storage. In block storage, again, I would stick to a standard NBD, TGT if you want SCSI, but for the most part, if it's your own client, like NBD is now already supported in most environments, stick to NBD. And at the back end, there are people today, whoever gets into this space, they end up implementing their own log-structured file system, and it is pretty hard. But if you want snapshotting like facility, you have to look at some log-structured file system. I did look at like a RocksDB, level DB based approach, but they are not so good in, they're good at storing simple key value store, but not so good for block storage. There is no good solution. You have to look at writing your own, but I would basically start with ditching snapshots and allowing users to just create many tiny interfaces, the tiny block devices themselves. Like in Docker root image allows you to basically version the images like using overlay FS. So the root file system is already versioned, which is equivalent of some kind of snapshotting. And for the data volume, which is like databases and stuff like that, you basically have the database continuously backed up, so you can get away from doing snapshots. You don't need snapshots, it's not a hard problem. You can basically keep the disk image as tiny images and sharded across. Instead of replication, I actually find Intel erasure code, they call it ISA-L, which is a user space erasure code library. We even have a Golang bindings because we needed that for Minio project. Use that and just break the data parts into data and parity. So in this, like say if you have 4 data and say 4 parity, you got only, it's like equivalent of replication, but any 4 drives can fail. So it really scales well and I get good performance. So object storage, I won't go into detail, but I actually see object storage to be the fast emerging one for storing unstructured data, because there is no POSIX. It's a certificate-based authentication, because I can't trust the root and other users on other systems. It's just a simple HTTP get put list and cert-based authentication. You can access it from anywhere across the internet. It cannot get simpler than that. It needs no special kernel extensions. And you can adopt the same ideas like from the file system, except it's just a stripped down version. And the cache is the one that is new. This is the last slide. Cache is actually, it used to be a tiny portion of the operating system, but nowadays it has become a big deal. Cache is the new primary storage in the enterprise infrastructure. More and more, the long-term data that has to persist goes to object storage, and the data that changes all the time is basically cached in NVRAM, in memory, or local hard disk, and they are usually managed by caching servers or databases. Redis is a common deployment nowadays. I see that just in-memory key value store, and once the operation is committed, they go to a database or it goes to an object storage. But the other ones are like the Varnish Squid. Tachyon is a HDFS caching layer, but it also caches Gluster and a bunch of other projects, object storage. But there is a new opportunity for caching project, because the new devices that are coming into the market, that these are persistent memory devices, they can scale up to terabytes, and any of the existing caching solutions are not that scalable. Like there is a scope for building a distributed cache, open source distributed caching server that is not just volatile, it is actually persistent cache. that can withstand machine failures and can reload and work, and at scale. So a project like that today will be a very hard project in the open source space. That's pretty much it. Sorry, I took most of the time. I'm bad at managing time. So I can take few questions and we can always talk offline outside. Thank you.
So let's see, we should have time for one or maybe two questions. Somebody here? Oh, there's one.
I'm a bit surprised to see persistent memory on that list. How would you? I've only seen it proposed really for for small amounts of data in transactions, so you can commit them and then only for the data that's in flight. How would you use it in a cache like that? Why do you think it would be very helpful?
Yes. So
Just a second, guys. This is part of the talk. So here are people wanting to learn something. So please be quiet when you leave the room. I know the schedule is tight, but please be quiet so we can hear the questions and the answers. Thanks.
So the question is, for a small amount of data, like say 4K data, small amount of data, I want it to be committed, but if you put it in cache, then there is no reliability. That's the question, right? How do you deal with that? Is that the question? Huh?
I've heard of persistent memory being used for small amounts of data that are transactions that are in flight. I have not seen it mentioned before for large caches like this. Why do you think it's relevant for a large cache or large file system cache?
That is because the size of the persistent memory devices now, these literally sit in the DIMMs, like standard memory DIMM slots, and they are in terabyte size. So the standard kernel memory managers would break down, like dealing with several terabytes of memory, even though they can address, like Red Hat has done a lot of testing on standard memory managers like that scale. But usually when you are talking at like persistent memory, their latency is not as fast as the real volatile memory. So these are new devices that are not as fast as volatile memory, but they are in nanosecond latency. Some of them are in millisecond. And the scale is, now you're talking about a couple of terabytes, right? And these are going to become commodity and built into standard motherboards in a matter of like few years. And this means that we need a new kind of caching. Basically, it's not like anything hard. We need to build new caching systems that are aware of that it's persistent and large scale. And at large scale, you like even simply moving from 4K to like 1 MB cache or 64, like 128K cache, the algorithms change a lot, right? Now you think about different issues. So there is today, because these are new initiatives, it has been the dream of operating system guys to converge memory and disk. It is non-existent today, but they are beginning to appear in the market. So the real thing is that they are arriving in the market at terabyte size to begin with. Okay, thank you very much.
Yeah, thank you very much. Thanks, Anand, for the talk.